On his 65th birthday, an investor withdrew an amount P from a fund of 1 million and withdrew the same amount on each successive birthday. On the date of his 82nd birthday, the fund was again equal to 1 million after the withdrawal. So the fund earned an annual effective interest rate of 10%, calculate P. So the thing here is that initially the fund had a million on the 65th birthday, but he immediately withdrew an amount P. So therefore, at time 65, what he eventually has is a million minus P. So let's consider 65 time as the present time at which we will collect everything. So if he withdraws a million, if he withdraws a P from the million at that time, so the present value at time 65 of his fund is a million minus P. So after this, there are withdrawals on every subsequent birthday. So which means there are withdrawals at time 66, 67, 68, up to 82. 82nd birthday is the last withdrawal. And so the 66 through 82, they form an annuity immediate. Let's call it K. K is the name of this annuity immediate that's happening from time 66 up to time 82. And each withdrawal is P. And the present value of this annuity immediate will sit at time 65 because we know that present value of any annuity immediate sits one period before the first payment. And remember, we are considering this part that starts at time 66. So one period before time 66 is time 65. The first one was lumped together with the present value at that time. So that's not our first payment of consideration. We are considering the ones that start happening at 66, and their present value sits one period before. So that's at 65, and that's what we want. And these are total of 17 payments from 66 through 82. So remember again, if we want to know how many numbers are there between 66 and 82, we subtract, we get 16, and then you always add 1. Because in the subtraction process, you lose one of the values. So 17 withdrawals between time 66 and time 82. And then that's not all. If these withdrawals were exhausting the fund, then we would say that the present value of these withdrawals equals this a million minus P, but they're not exhausting the fund. He still has a million after this last withdrawal on the 82nd birthday. So that million also contributes. So this initial present value of a million minus P, that should equal the present value of this annuity K plus the present value of this million, which he has in his account on his 82nd birthday. So the equation of value would then be, this is the beginning present value after you made that withdrawal of P, a million minus P, and that should equal the present value of that annuity K, which would be 1 minus 1 plus I powered negative n. Remember that annuity had 17 payments between 66 and 82 time. So 1 minus 1 plus I to the negative n over I times P. P was each of the withdrawals. Plus, and then we also need to pull this million back through 17 periods because there are 17 periods between 65 and 82. This million was the value of the account at time 82, and you pull that back to 65, which is our reference present value. You pull it back 17 periods, so you multiply it with 1.1 power negative 17. So that's the equation. The initial present value of million minus P equals the present value of the subsequent annuity plus the present value of the account value at the end. Okay. And so this million times 1.01 to the negative 17, that gets subtracted and the P gets added on both sides. And this left quantity is 802.155. And here, when we simplify this, it's 8.02p. and then plus P makes it 9.02P, and then when you divide, you get P equals 88,915. That's choice B.